Hello, we are Team Coco, and we will be presenting our machine learning project, the Real-Time American Sign Language Translator. According to the World Health Organization, there are 466 million people that have severe hearing loss. To be able to communicate with those that have this disability, sign language was developed. Unfortunately, like with vocal languages, there are a variety of sign languages that developed in different parts of the world. This can be very limiting when it comes to international communication, with no solution other than learning and studying the alternate sign language online. However, with the use of machine learning and convolutional neural networks, we can develop a real-time sign language translator, and we will be covering its use with American Sign Language.
A common way of tackling pose classification is to use landmark detection in addition with a position algorithm. In the case of American Sign Language translation, landmark detection would detect key points in my fingers and palm. Here in this video, I use a model from the OpenPose library to map out the key parts of my right hand. After the key points are mapped out, a human-made algorithm would classify the gesture. This is the sign for the letter C. The algorithm would measure the distance and angles between these finger landmarks, and if it fits the parameters the programmer set for the letter C, it would then output the letter C. There are problems with this method, however. One is that landmark detection isn't perfect. As you watch the video, you can see that it does a solid job, but there are some hiccups. Sometimes it would map parts of my eye or parts of the background as a landmark, which would obviously cause problems for the algorithm. Also, a human-made algorithm would be time-consuming to create, especially if one wants to create a translator for multiple words. This method would also require the signer to be in a particular position in front of the camera, which can be cumbersome and inconvenient to the user.
As for our dataset, we will be utilizing 600 images of American Sign Language letters A through E, coming from Kaggle datasets as well as our original submissions. The data will be split into 75% and 25% as training and validation datasets, respectively. In terms of pre-processing, we began by resizing all the images to a size of 128 by 128, followed by the addition of minor zoom and rotation in order to prevent any overfitting in the model. Batch normalization was also applied to the dataset in hopes of increasing the model's speed and performance.
The bare minimum for a baseline is a random guess approach. For our project, the base accuracy would only be 25% since there are only 5 classes. This can definitely be improved upon. After the data is pre-processed, it will be split up to test and train our model. Our model starts with MobileNet. We wanted to use a pre-trained model that was quick and efficient because we envision our real-time American Sign Language translator to run on a personal cell phone. MobileNet alone wasn't producing the accuracies we wanted, so we added dense layers that would improve the accuracy. We also added dropout layers to combat overfitting. After the model is trained, we did some testing with a live video feed. The way this works is that the frames from the video feed are pre-processed in a similar way to how we trained our model. These pre-processed frames would then be given prediction values from our model, and the category with the highest prediction value would be displayed on the screen. The final results of our model were promising. We were able to get accuracies up to 92%. We found that training the model to 43 epochs was the most optimal because the model starts to severely overfit in the late 40s. From the confusion matrix, we could see that our model has a bias towards the D sign. We calculated that the D class has a precision of 0.54 and a recall of 0.94. This low precision score and high recall score means that the model is categorizing gestures as D too liberally. We theorize this is because the D sign has multiple features in common with the other signs. It has a vertical feature like the B sign and a rounded circular features like the A, C, and E signs. Here is a video of our model working on a live video feed.
Should this project go further, we plan on working to include more classes, the letters F to Z, into the dataset, as well as incorporating the model into a functioning phone application. One possible route would be through the use of Kivy, a Python software used for the development of phone applications. And we thank you so much for listening.